Find the volume of the solid obtained by revolving the region bounded by the graph of f of x equals 1 over x and the x-axis over the interval 1 to infinity about the x-axis. All right, so here's a problem which brings together a couple of ideas that we've learned in the class. The concept of an infinite limit, which is what we learned in this section, but then also rotating a region around an axis, which is what we learned early on. So the best thing to do is first get an idea of what the region looks like. So we have the function 1 over x, which looks like this in the first quadrant. And we're only on the interval from 1 to infinity, so let's just say this is 1, and then since we're going to infinity, I'll just shade going that direction. And we're rotating around the x-axis. We're rotating this way. Now, what does that mean in terms of a method to use here? Well, if you'll recall, if we use a vertical rectangle, which is usually a good idea, that would be perpendicular to the axis of rotation, which would mean we would be using the disk method. So the disk method looks like an integral from the lower end point to the upper end point, which would be infinity in this case, of, if you'll recall, it's pi r squared, so pi, just thinking of integrating the area of a circle. So it would be pi. The radius is going to be the height of this rectangle, which is determined by the function 1 over x. That gets squared, and then we're integrating dx because we have a vertical rectangle. So in order to work this out, because this is an infinite limit, we'll have to rewrite this as, I'll just pull pi out and call it limit as t goes to infinity from 1 to t. And instead of writing 1 over x squared, I'll make it x to the negative second dx. All right, which we can integrate as a function. So I'll just leave pi out front for a moment. X to the negative second, when I add 1 to that exponent, that gives me x to the negative first over negative 1, and that will integrate from 1 to t. I'll go ahead and pull this negative out front, so it's going to be negative pi times the limit as t goes to infinity, and this would be 1 over t minus 1 over 1, which is just 1, so minus 1. All right, now as t goes to infinity, 1 over t, this right here would go to 0. So essentially I have negative pi times negative 1, which means that this rotated volume would be pi. All right, so basically the same problem that we did from earlier, but the setup was a little bit different because we had to do the disk method. And that kind of has an interesting result in that we were looking at regions that were infinitely sized, but then have finite area. Here we have a region that is infinitely sized, but then also has a finite volume. So that's an interesting situation there. Okay, the next problem here, evaluate the integral from negative infinity to 0 of 1 over x squared plus 4 dx. State whether the improper integral converges or diverges. Okay, so to evaluate this, notice the lower end point is infinite here. So what we would do is set this up again as a limit as some variable t goes to infinity, and we'll just let it go negative t to 0. All right, and that's just fine. Then we're integrating the function 1 over x squared plus 4 dx. Now the function 1 over x squared plus 4, when I integrate that, you should recognize this from integration techniques, that this is the form of the arctangent. So when I integrate this, I will have the limit as t goes to infinity of the arctangent, but because this term right here is 4, we would say a is 2. All right, so it's 1 over a, so it's actually 1/2 times the arctangent. And then it's x over a, because it's always the function u over a. Well, a would be 2 in this case. But it would look like that, is my ultimate point there. All right, so now we are integrating here from negative t to 0. And some of you might be wondering, can I let t go to negative infinity and just call this t? You can. It doesn't make a difference in the end. I choose to use negative t to 0 just because the lower end point is smaller than the upper end point. It ultimately doesn't matter. It's fine either way. All right, then let's see. If I plug in these endpoints and I bring out that factor of 1/2, I've got 1/2 limit t goes to infinity, and it would be arctangent. When I plug in 0, that's just going to be 0. 0 over 2 is still 0, minus the arctangent of negative t. All right, so what happens here? Well, arctangent of 0, you should know, or you should be able to figure out either using your calculator or a unit circle. The arctangent of 0 is 0. The arctangent of negative t, you might have to grab your graphing calculator to see what the graph of arctangent looks like. Ultimately, it looks something like this. You have sort of like an S-curve. But the interesting thing about this, it kind of looks like x cubed. But the square root, the cube root of x, sorry if I could say that properly. But it's bounded below and above. And those bounds are usually the important parts to remember about arctangent. It's bounded below by negative pi over 2 and above by pi over 2. So it approaches these values, but it never reaches those values. Here's arctangent of 0, which is 0. Okay. Another important point is arctangent of 1, which is pi over 4, because that's just where sine and cosine agree with one another. Anyway, as we let the arctangent function go to negative infinity, so as we let arctangent go to negative infinity, what we're doing is observing where this function's going that direction. And it's going to negative pi over 2. So this is approaching negative pi over 2, which means I would have 1/2. So this would be 0 minus negative pi over 2. So really just positive pi over 2. So that would approach pi over 4. So that means this limit converges to the real number pi over 4. All right, I have another example for us here. This one using a logarithmic function. And we have both endpoints being infinite. Okay, so when we set this up, the thing about having both endpoints being infinity is it's probably a good idea to just split the problem up into two separate pieces. Because if you'll notice, we've always done two separate pieces here. You essentially do the integral, okay? And then once you actually do the integral, then you plug in the endpoints and then handle what's going on with infinity. So let's take that approach here. And it's going to be doubly useful here because you might recognize this function. It's a product of an algebraic and an exponential, which means that we would need to use integration by parts to actually do the integral. So let's just split this up and do the integral first. All right, so I have the integral x e to the x dx. For integration by parts, I choose something to be the value of u, and if you'll recall the ilate, so inverse trig, logarithmic, algebraic, so that means I should choose x here for u, leaving dv to be e to the x dx. The derivative of u is just dx, and the integral of v gives me just e to the x. Okay, so this is equal to u times v minus the integral of v du. So even though it's integration by parts, it's really not too bad. So minus e to the x, and then technically plus c. It's not going to make any difference in the end, but I'll go ahead and tack it on. Might be helpful to go ahead and simplify and express this in this way by factoring out e to the x. Okay, now let's handle the limit. All right, so the limit here, we would be doing the limit as t goes to infinity. Both endpoints are going to infinity. You can split this up into two separate integrals, and that's what the rule stated earlier in the text. To be honest, I find it's just fine to leave it as one and just allow it to go between negative t and positive t. Now, if you were going to do the limit as t goes to positive infinity and then the limit goes to t to negative infinity, sure, you have to split it up. But this is the way I've always done it, and it works just fine. And we have x e to the x dx, but since we've already integrated that, we'll just bring that result down. So it's e to the x times x minus 1 evaluated between negative t and positive t, which would be the limit as t goes to infinity of, it's going to be a lot here, e to the positive t times t minus 1 minus e to the negative t times negative t minus 1. Now, if I factor out a negative from the second portion, that might make it a little bit easier. It would be nice if it would simplify more, but unfortunately, because it's e to the t on one hand and e to the negative t on the other, I won't be able to combine much through multiplication. However, I can, like I said, factor out this negative and make this plus e to the negative t times t plus 1. Okay. Now, evaluating this limit. So you might think that it's rather obvious, but you've got to really be careful with infinite limits. So the thing is, the function e to the t, let's look at its graph. So e to the t, its graph looks like this. So as we go to positive infinity, clearly the function e to the t goes to positive infinity. So this part, as t goes to infinity, is going to infinity. And then t minus 1, as t goes to infinity, that's also going to infinity. So we have infinity times infinity. Then, as we let t go to negative infinity, e to the t is going to 0. So this becomes 0 here, and then this would stay infinity. So you might be thinking, all right, so infinity times infinity, that's clearly infinity, and then 0 times infinity would be 0, so infinity plus 0 would give you infinity. And you've really got to try not to do that sort of thing. Because sometimes the logic actually will work out that way. Sometimes it won't. You've got to be careful with infinities, okay? Because it's not a number. It doesn't share the same properties as numbers. You have to look at them as limits. So for instance, I would agree with you, infinity times infinity would result in something that's even more infinite in value, especially since pretty much we can count on everything being positive here. All right, so I don't have any issue with that. What I do have an issue with is 0 times infinity. Because the thing is, if I rewrote this as t plus 1 over e to the t. As t goes to infinity, this is now technically infinity over infinity, which is an indeterminate form according to L'Hopital's rule. Or I guess that means that L'Hopital's rule would apply. And that's the safest way of evaluating this function, is using L'Hopital's rule. So we might want to kind of go to the side and evaluate that using L'Hopital's. So limit t goes to infinity, t plus 1 over e to the t, using L'Hopital's would give us the limit as t goes to infinity of the numerator would become 1, the denominator would be e to the t, and then this right here, this limit would go to 0, because the denominator is growing, but the numerator is not. All right, so it does in fact go to 0, but we probably do need to think about that in terms of L'Hopital's rule instead of just trying to logically say 0 times anything is 0, because that's not always the case if one of those terms is infinity. It depends on how quickly they're going to 0. All right, so since this is going to 0, and this is going to infinity, I think it's safe to say that this entire thing is going to infinity, which means that this limit, or the integral, diverges.